Hey, what's up, bud?
Hey, how's it going?
It's going. We'll see how the all online goes now.
Yeah, it shouldn't be too bad.
Yeah, not much different. Just even more time spent in the house at my desk. Same place.
Pretty much.
Mm-hmm. Hey, Dr. Shortish.
Hey, Christian.
Hello.
Set it up. Yeah.
Oh,
I don't see both of you. It's my side or is it you guys?
Oh, no, I just didn't have my video on.
Okay, that's fine. If you want, you can switch it off. It's just I was making sure.
Oh, no, it's okay. I've been messing with that code for the last week, and for some reason I can't get it to really converge. I got it to where it starts converging towards if I make more increments, it actually reduces, and it looks like it's coming down to a limit. But then if I add more circles, then it keeps increasing. So I don't know. Still working with it. I think there's something in the math. I might talk to Dr. Kochik and see if he can help, because yeah, there's something with the integration and multiple variables where it's not working correctly.
Yeah, let me know when you want me to look at it. Yeah.
Okay. Yeah, it's tough to. I know you don't use MATLAB, so I don't want to just kind of send you the file. I don't know how the best way would be. Are we still allowed to come in? Like, could I come to your office hours on campus someday, or am I not allowed to come at all?
I think you can just today. Avinash showed up, so.
Oh, okay.
So I don't know what the rules are.
Yeah. Okay.
Hello, Gordon.
Hello.
It's a nice background. Is this your painting? Do you paint?
Me?
In the background, I see a lot of painting.
Oh no, they're just random posters that I have.
Random posters. Okay, nice. Oh, we have Curtis too. Let me set this up. So I posted homework 12 very late. It was posted only today morning. So I made it due December 4. It was supposed to be earlier. I said it was Wednesday. But you should be able to work on this right away. It is all concerned with stuff we did last week. So you should be able to right away proceed work on. You have a final exam. It will be available So it's a take home. Take home. So it will be available during weekend. Probably even by Friday, it depends how much I can work on it. And it will be due latest by Sunday, let's say, Sunday evening. And it will be due on December 11, 4:45 p.m. Now, I should point out that in case you have any questions related to the exam, you will have to write to me in advance. So obviously, if you send me an email at 4 o'clock and say that you would like to meet me, that doesn't work. So since I'll be posting the exam reasonably early, if there is any confusion at all, you have to send me an email and then we can fix the time. There won't be any official office hour during the last week of or during the week of exams. Is that clear? And there's one more thing, and that is course evaluation. So course evaluation is available on D12. So since few semesters, the university is doing the course evaluation on D12 instead of paper distribution in the classroom. I'll encourage you guys to do that. I surely look into it. It's usually benefits me reasonably, but university also uses it. So just as a duty, try to do that, but I cannot force you guys to do that. So it's nice to get that done. Hopefully it doesn't take too long. I think usually there are only 5 to 6 questions, so get that done if possible. Okay. Any other questions I might be missing? Okay. Okay, so we introduced conservation equations that were derived from Maxwell's equation, and here this week I want to do some applications related to that. Today I'll start with a very reasonably simple application, and since especially the momentum tensor is actually a tensor, it is good to have a feel for how it works. So let me start by reviewing. So we have Maxwell's equation, of course. Maxwell equations. Is this readable? Should I change the pen by any chance? Readable?
It should be good.
I can read it.
Okay. So Maxwell's equations read divergence of displacement. Everything is in position space here, so that's equal to rho. Then we have that the magnetic field is equal to 0, and the constitutive relations are D is equal to epsilon naught E, and B is equal to mu naught times H. That's your divergences, and the cross product or the curl of the electric field is equal to the negative time derivative of the magnetic field. That's Faraday's law there. And we also have del cross H equal to time derivative of the electric field plus the current density. So that's your Maxwell equations. Then we saw some conservation equations. conservation of loss if you want. And that's what we want to do today. One is charge. In fact, it's charge density. So it's time derivative of charge density plus the divergence of the current density is equal to 0. So equal to 0 means that actually the charge is really conserved at every point in space. So this J is called the flux of charge density. We have energy conservation given by rate of change of energy density, U, plus the flux of energy density, that's called the Poynting vector. And whatever is lost, whatever is not caught in the tube is actually J is the energy lost into the charges. So this is the work done on the charges per unit time. So it is a power vector. So this is equal to 0. I'll define U and S in a minute. And we also have momentum conservation. And that's given by rate of change of momentum density, G, plus the flux of momentum. That's a tensor now, and that's the equation we will use today. And that's identified with force density. Notice the language. This is charge density. J is the current density, of course, but it is the flux of charge density. That's the way to look at it. The flux of charges is what current is. This is energy or energy density. This is the flux of energy or flux of energy density. This is momentum density. This is the flux of momentum density. S is also called Poynting vector, and T is also called the stress tensor because it has connections within fluid dynamics. We talk about stress and strain. And the third piece in the energy is the work done, rate at which work is done on the charges. That is how you convert electromagnetic energy into motion, if you want. And similarly, here the third term is the force acting on the charges. What are U, S, and G? So we have the electromagnetic energy density is 1/2 epsilon naught E square plus 1/2 mu naught times V square. That's the standard relation. This is nicely captured as a dot product. So this is E dotted with D plus 1/2 times H dotted with D. That way the symmetry comes out nicely. So that's energy. Flux of energy is the Poynting vector. That's S, which is E crossed with H. And we have G to be equal to D crossed with B. That's a momentum against a vector. Now stress tensor, or the flux of momentum, energy, flux of energy, or energy, it's all densities, momentum, flux of momentum. Now this is the new feature this is a tensor now, and we should make sure that we learn how to use this. This is U. This is the same U here times 1. This is a double vector. We have introduced this before, and minus of E and a D, but this is not dotted. So this is important that I stress that this is not a dot product. These are two different vectors, so we should use it in that form, and we will use that today. Because this, again, it depends on whether I take the dot product from the left-hand side or from the right-hand side. Okay, so that's our conservation laws, and we would like to use this in some scenario. So let's take a very simple scenario of a capacitor, right? Parallel plate capacitor. A parallel plate capacitor, we will represent it as, so this is one of the plates, that's the second plate, and that's your junction. So these three dots mean that they go all the way to infinity. Let us say this is a conductor on the left-hand side. So the whole space, whole half space on the left-hand side is a conductor. That means to say electric field is 0 everywhere inside the conductor, and magnetic field is also 0 everywhere on the left-hand side. On the right-hand side, again, we have a conductor. So electric field is 0, magnetic field is 0. So those two are true. Now this plate itself, let us say, has a positive charge on the left-hand side. And on the negative side, on the right-hand side, we have a negative charge. Both are equally both are uniformly charged, and they have the same amount of charge on the left and right, and so there will be an electric field. So we have an electric field going from here to here. So they start from the left and go to the right. So everywhere in between, the electric field is a constant because it's a capacitor. And let's say that's the z hat direction. And it's a constant E. So let's figure that out, what that E is. And let us also say magnetic field is 0. So overall, we have magnetic field 0 everywhere. And electric field is equal to, first of all, what is the electric field? So you would say you would actually draw a box, correct? So this is how you would calculate the electric field for a parallel plate capacitor. Remember your Gauss's law. So that's a pillbox. You can make it a cylinder if you want. So Gauss's law tells us that E dotted with dA over a closed surface. We chose that box to be the closed surface. That's equal to the charge enclosed inside in here. And charge enclosed is, if this is, let's say this is a uniformly charged plate. So we have sigma times whatever is the area, right? This is charge per unit area. So that's times area. And divided by epsilon naught. That's our Gauss's law. Since it is a conductor on the left hand side, electric field is 0, so that doesn't contribute. So there is only one side of this whole surface that contributes, and that is E times A. So that's sigma times A over epsilon naught. So electric field is sigma over epsilon naught. Okay. So what we have is electric field is equal to Z hat times sigma over epsilon naught if Z is less than A and greater than 0, right? That means if it is, and I should say this length, let us say, is A. Distance between the plates, let's say, is A. And it is equal to 0 outside. Otherwise. That's our magnetic field and the electric field. We would like to calculate now. Let's a question we can ask is, so this is all. So this is what is given to us, and this is all static. And the question we can ask is, what is the force on each of the plates? Correct. It is clear there will be a force because this will try to attract that and that will try to attract this. So what is the force? In fact, it is better to talk about force per unit area. So there's a pressure on this plates. They will try to squeeze themselves. So let's ask what is that force. So let me change the code. So try to have the picture in your notebook because I will have to refer to that. And when I move it, you won't be able to see that. Okay. So to address the question of force, so let's consider the momentum equation, and we have time rate of change of momentum density plus the divergence of the flux of momentum density plus the force density is equal to 0. This is the force density. So we would like to calculate this force. Right away, it is clear that G is equal to D cross B, which is equal to 0 because B is equal to 0. So G does not contribute right away. So we have F, force density, is equal to negative divergence of this flux of momentum, flux of momentum density. Let me draw this again. So that's your picture there. That's your electric field. And now I have to integrate this on a volume similar exactly like we work in the Gauss's law. Let's, since I'm interested in the force on this plate, let me find the force on this box. So that's a box, that's a pillbox. And if you want, this is cylindrically shaped. And let us say this is delta. So this is delta. That's also delta. 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 At this point here, that's z equal to 0. And at this point here, that's z equal to 8. So first find the force on this plate, then find the force on the second plate. So that's two things. So let's integrate this on this volume. So you will do d cube r times force density, force per unit volume times the volume itself. That's the force. That's a total force on this particular volume. Minus of integral d cube r times divergence of t. So that's the volume V we are talking about. That's the volume V we are talking about. This is force on this volume, right, on that volume is equal to, this is an volume integral of a divergence of a vector. We immediately use divergence here, correct? So this becomes on a surface. So this is a surface integral, a closed surface integral, exactly like Gauss's law. But the only difference is that now this is a vector, not just a vector, this is a tensor. So we have to be careful there. So that's dA dotted with T, where this closed integral is on the surface of this one. So that's what the force would be. Let's introduce our T. Notice that T will be equal to 0 on this side. So T will be equal to 0 for z less than 0. And it will be equal to u times 1 minus E times D. That is, B is 0, so maybe I should write this better. So first let me do U. So first is U. U is 1 by 2 E dotted with D plus 1 by 2 H dotted with B. But that's equal to 0. So that's not there. And that's the first term is nothing but epsilon E squared. That's your energy, if you want. That's nice. And T, the flux of momentum, it's a dyadic. It is equal to U times 1 minus of E times D. Notice this is, these are two vectors, and minus of H times B, which is 0. Electric field is in the z direction. D is epsilon naught times E. That's also in the z direction. So what we have here is U, which is 1 by 2 epsilon square in all x. Remember, 1 is x hat plus y hat plus z hat. That's what it is. And here we have minus epsilon naught e square times z hat. That's equal to, let me write it more explicitly, use this from here. So I have 1 by 2 epsilon e square x hat plus y hat plus z hat, and subtract out. We could have done this later also, but we're processing this here so that this integral gets easier. This is the same as this one is plus and minus. So what has happened is that 1 by 2 epsilon naught e square, and this remains x hat. This remains y hat. And when I take this out, so there's a 1 here, there's a minus 2, so that's a minus z hat. So there's an asymmetry in here. There's a minus z hat. Great, so that's good. So we put that in here. Right? Notice that T is equal to this quantity only in between the plates. This is also, I should also point out that this is equal to 0 outside the plate. That means to say for z less than 0, it is 0, and z greater than a, it is equal to 0. So the force on the left plate, so this is the force on the left plate, is negative integral of, on the left hand side, this is equal to 0 because there is no t to begin with. So it's only the right hand side that shows up. So it is dA times z hat. That's a normal vector associated with the right hand side, dotted with t. But t is that, so let's write that out. So this is equal to x hat plus y hat minus z hat, and I'll write the 1 by 2 epsilon naught e square. That's nothing but u, right? So I'll just write it as u. So this is nothing but u. Which is a constant, right, inside the plates. Clearly, z dotted with x is 0, z dotted with y is 0, and z dotted with z is 1. So this is equal to minus of, there's a minus sign here, which makes it a plus z hat times u. This is a constant everywhere inside the area. So this is nothing but area. So what we have is force per unit area. The force on this box per unit area, that's the area of that pillbox that's facing into the capacitor. That's equal to, it's in the positive z hat direction, and the magnitude of this pressure, force per unit area, is actually the energy, where energy itself is epsilon e squared. This is not energy, I should say, point out that this is energy per unit area. Dimensionally, it is correct because if I were to multiply by a distance in the numerator and denominator, force times distance is energy, so energy per unit volume, so that's energy per unit volume. So the pressure that's acting on this plate, the attractive force, is exactly equal to the energy density. We could have repeated the same thing on the right-hand side, so let's quickly do that without actually going into the details. It should come out to be negative, right? So it's not very obvious as to why that negative sign will come. Mainly it is from the normal vector. So everything remains the same. This will stay here, except now when we write dA, what will change is that this time the normal vector is in this direction. dA here would be minus z hat direction, and that changes the sign here, so that will be equal to minus z hat direction. So this is on the left plate. So this is on the left plate. If we were to do this on the right, right, you get the same force per unit area is equal to minus z hat. Right, which is almost identical work that you have to do. That's good. So now we know force per unit area. Let's also quickly see what about the energy conservation equation. So let's see if energy conservation works in the same way as we want, just to make sure. So this is energy conservation equation tells that rate of change of energy density plus the flux or the divergence of the flux of the divergence of the Poynting vector plus J dotted with E. This is the rate at which work is done by the electric field on the charges. But most of this is zero because S is equal to 0, and that's because E crossed H comes in. So that's equal to 0 because H is equal to 0. There is no J in here. So since J is equal to 0, J dotted with E is equal to 0, and that's because there is no current. There is no current either, which means that derivative with respect to time of U should be 0, and that is indeed 0 because 1 by 2. So U is equal to 1 by 2 epsilon naught E squared as we calculated here, but that's constant, right? That's uniform inside the plates, but this is only inside of the plates, right? So this is inside the plates and 0 outside. So clearly, time derivative, so since it is a constant, that's U by dt is equal to 0. But we also know that force actually is a gradient, right? Force is also the gradient of energy, right? In this case, if we think of this as force density, should be the gradient of energy density. So is that can we make some connection with this? The derivative here is a virtual work that is done, right? So it has to do with the distance between the plates. So we will define force per unit area should be or let's let's first calculate the total energy. Right? Yeah, so let's think of it like this. So force should also be equal to negative rate of so negative derivative with respect to A, right? So I'm having a distance A and I move it slightly, I increase the A a little bit, and I ask how much does the change in energy, what is the change in energy due to that? And that will be defined as a force. So this is total energy. But total energy is easy to calculate. So that's minus derivative with respect to A. Total energy is U times volume, right? So U times, that's 1/2 epsilon naught E square times the volume, which is easy. That's area times the length. So that's the volume of that box. And clearly, force per unit area is equal to, there's only one length, this is a constant, so that's minus 1/2 epsilon naught E squared. The negative sign means that it is an attractive force. How do you see that? So notice if I were to plot this energy, so this was the energy with respect to A, it is 0 when A is equal to 0, and it actually grows linearly. So it is clear that if you were to drop something here, so the force is, so its tendency is to fall down. So it tries to go in. So that's your total energy. Total energy. So so the tendency is for it to go down. So that means force per unit area tries to decrease it. So it is indeed true. So this is an attractive force. So this is an attractive force. One could also think of, we won't do that here. I think that's only 7 minutes remaining. One could also imagine, I'll just mention it here. So instead of having positive and negative charges, one could have a current of positive charges coming out of the board. So this is a current of positive charges coming out of the board. These are positive, so this is J. J that is coming out of the board. And I could have another current going into the board. Current naturally means that there is a charge associated with it. So this is positively charged, so that's positive, and that's negative. So there will of course be electric field that goes this way. But now since there is a current, there is also a magnetic field going that way. And that's an interesting configuration now, because now the momentum is not equal to 0, right? So that is an E crossed B. So here B comes out to be equal to, so there's a velocity associated with this current. This comes out to be exactly, so C times B is actually beta crossed with the electric field. So there are 3 directions, so there's a velocity, right? Beta is equal to V over C. That's the velocity with which this current is coming out of the book. So that's your 3 configurations. And again, you can do this whole analysis, right? That's in this case, that will be momentum also. But the interesting part is that since there is a velocity V, you can always go to the rest frame of that velocity, of that frame. And then it becomes the usual problem that we just now did. But we won't analyze this here, but I'll just mention this, and probably next semester when we do relativity, we will talk about this there. At this point, I will stop here, and next time we will do the same thing for a sphere. Right now, this is for parallel plates. We can actually keep a charged sphere and ask the same thing: what would be the pressure on a charged sphere? So I'll stop here. So we have 5 more minutes, but I'll stop here. And if you have any questions, let me know. That's all. Thank you.
Thank you. I'll probably email you and see about setting up a time where I can come in and talk about the MATLAB, if that's okay.
Since you want to show me your program, isn't Zoom better for this purpose?
Oh yeah, I could just share my screen if you want.
Correct. Then you can share your screen, and we can. Then you can actually show me in detail, right? Isn't that better? I'm just wondering, right?
Yeah,
Otherwise,
that'd be fun.
Yeah.
Mhm.
So let's do that on Zoom, and whenever you want, let me know which.
Okay, I'll send you an email.
Sure. Okay.
Okay, thank you.
All right. Have a good day.
Yeah. Have a nice time.